Hello. In this video, I'm going to be going through paper 2 from ACE Physics Syllabus Code 9702. This is paper 23 from October-November 2014. For my students, we've been studying waves for a few weeks now, and this would be a good question, number 7 from that paper, to really assess how well you've mastered a few of the learning outcomes that are associated with waves. Namely, in this paper, we'll be looking at the learning outcome, describe the motion of transverse and longitudinal waves, and describe waves in terms of their wavelength, amplitude, frequency, speed, and intensity. So really those two learning objectives. We'll take a chance also here where we discuss phase difference to talk about how this is really a key idea to making sense of the more recently introduced learning objectives related to wave interference. So if you want to, make sure that you've got this paper in front of you. Attempt to work through the paper as best you can. Pause the video, and then once you feel like you've got your best answers down on paper, go ahead and hit play and check your work against mine. All right. Question 7, it reads, explain what is meant by a progressive transverse wave. And first, we're asked to explain progressive. One of the places where we're heading with this study of waves, and particularly with wave interference, is that if we send, say, a disturbance through a medium, and then that disturbance is reflected at a boundary, well, then that wave can actually, that reflected wave can come back and it can interfere with itself. And that type of wave has a special name. It's called a standing wave. And so when we talk about a progressive wave, those are the waves we've been studying. We haven't studied standing waves yet. And so a progressive wave is just one that is transferring energy from one place to another. Standing wave, as the name kind of implies, is stationary, and so it doesn't transfer energy. And so a progressive wave transfers energy. I'm just putting the key idea down, but you would want to actually write a complete sentence with that. A progressive wave is one which transfers energy, from one place to another. But the key idea is that progressive waves transfer energy, whereas stationary waves do not. Transverse, we know that relates to the learning outcome being able to describe the motion of transverse and longitudinal waves. And so a transverse wave, let's go ahead and put this one in a complete sentence here. Explain what is meant by a progressive transverse wave. And so for transverse, we can say, a transverse wave has particles which move perpendicular to the direction of energy transfer. So the wave is transferring energy, and if the particles move at right angles to that direction, we call it a transverse wave. Part 2 here says define frequency. How frequently do the waves occur? Okay, so it's happening per unit time. So it is the number of waves, number of oscillations, number of cycles. These are all sort of interchangeable. Number of waves per unit time, waves per second. All right. Now here it says the variation with distance x of the displacement y for a transverse wave is shown in figure 7.1. On figure 7.1, 5 points are labeled. Use figure 7.1 to state any 2 points having a phase difference of 0 and 270 degrees. Let's take a moment to sort of remind ourselves of this idea of phase difference. And so when we look at sort of like an entire waveform, that wave sort of goes through a phase, and sort of like a quarter of the phase, halfway through, 3/4, 4/4. And so sometimes we can talk about phase difference, or the phase of the wave, sort of in fractions, of a cycle. Well, if we divide that, up enough into 360 even sort of equally spaced parts of the wave, then each one of those would be a degree. And so we say that there are 360 degrees sort of in this wave here. A phase difference then of 0 would be just an equally identical point. Okay, and so like point P would be have no phase difference with itself, but it tells us to state any 2 points, and so we can't sort of offer the same point and itself. We'd have to look for another point that is has no phase difference. And so if we look at sort of the choices that we're given here, points P, Q, R, S, and T, we can see that there's only 2 points that are one sort of wavelength away, right? And we know that a wavelength is when we're going to get to an identical sort of point, sort of one wave over. And so only points P and T have a phase difference of 0. They're the only points that are sort of given that are entire wavelength apart from each other. Now, 2 points that have a phase difference of 270 degrees. If we start at the initial point P that's labeled here, we can kind of count out how, what's the phase difference. If we've gone from a trough to equilibrium, well, that's 90 degrees. If we go from a trough up to a crest, that's 90 and another 90, or 180 degrees. These things are sort of an antiphase, we say. They're out of phase with each other. And here's where the idea of phase difference becomes so helpful when we're trying to make sense of interference, because we know, for example, that we will get destructive interference if 2 coherent waves meet and they are 1/2 of a wavelength sort of away from each other. If their path difference is half a wavelength, their phase difference is 180 degrees. Okay, so we can sort of express how much off one wave is from the other in terms of a phase difference, in terms of degrees or even radians. And so we can say 360 degrees or 2 pi radians is an entire waveform. Or we could express it in terms of a path difference, and so we know that, well, if one wave is half a wavelength off from the next one, then by the time the crest from one wave makes it there, it will be the trough of another wave, which is 180 degrees of phase different from its neighboring wave, or half of a wavelength. Again, either path difference or phase difference, 2 good ways to sort of think about that and how that leads to either constructive interference. For example, points P and T are both at troughs, and so if they were to meet and superpose, then we would get constructive interference, right? So we'd get a trough, and a trough would be sort of like a double trough, right? So what are 2 points that are 270 degrees away from each other? Well, we said P and Q are 90, P and R are 180, and so if we keep going there, then we'll get to 270, 90, and another 90, and another 90. So points P and S are 270 degrees away, right? Go another 90 and we get to 0 again, or 360 degrees. It's important to kind of remember that a wave, it repeats, right? And so all of those sort of multiples of 0, 360, and so on. Likewise, we could have said that points Q and T are another sort of acceptable answer for this, right? Because Q and T also have that phase difference of 270 degrees. Or Q and T. Either one would be acceptable. Now we need to, for part C here, the frequency of the wave in B is 15 hertz. So they tell us that. Calculate the speed of the wave in B. The speed of the wave, we think about it as its velocity, which is equal to wavelength times frequency. Because they've given us the frequency, we really need to just deduce the wavelength. Because we're given a plot of displacement against distance x, then we can really just sort of read off the wavelength on this plot. So we know it would be the distance from P to T here, but it looks like the wave also sort of starts at a crest, and then we can see that a crest here neatly intersects at 1.2 centimeters. And so we can just read off that the wavelength is 1.2 centimeters. If you had this paper in front of you and you were able to calculate the wavelength between, say, points P and T, or there's several other sort of clever ways that you could think about deducing this, then good job. 1.2 centimeters is the correct wavelength. And so here we're going to calculate the speed of the wave as 1.2 times 10 to the negative 2, so this factor of 10 is the same thing as centi. So 1.2 by 10 to the negative 2 meters, or 1.2 centimeters, times the frequency of 15 hertz. Calculator check. And I've got mine right here. So we've got 1.2 times 10 to the negative 2 times 15 gives me 0.18 meters per second. Part D of this paper reads, two waves of the same frequency have amplitudes 1.4 and 2.1 centimeters. Calculate the ratio. The intensity of the wave of amplitude 1.4 centimeters over the intensity of the wave with amplitude 2.1 centimeters. So the learning objective described waves in terms of their wavelength, amplitude, frequency, speed, and intensity. Here we really need to remember the relationship between intensity and amplitude. Intensity is proportional to amplitude squared, and the maximum displacement is the amplitude there. All right, but for this question, the amplitude is 1.4 and 2.1. And so all we really have to do to get the ratio of the intensities is calculate the ratio of these amplitudes squared. So our calculation is 1.4 centimeters squared over 2.1 centimeters squared. The centimeters will cancel. Calculator check. Got mine handy right here. 0.4 repeating.